Alright, so this is the second video in the conic definition series. I did say previously that it was going to be 4 videos, but I've decided that I'm going to group circles and ellipses together because, a circle is an ellipse in the same video. So, again, same thing as the last video. I'm just going to basically go over why circles and ellipses are the shapes that they are and the key features of those shapes, which are really important in order to understand fundamentally understand conic sections, and then it's also a common test question. So, like in any other conic section, circles and ellipses are both formed, well, I'm just going to start with ellipses for now. Just ellipses in general. Ellipses are formed when a plane cuts through a cone. All conic sections are formed when a plane cuts through a cone. But when a plane cuts through the cone in a way such that it only cuts through one cone, one of the two cones in this double napped cone, at a certain angle, and it doesn't intersect the base, it's going to form an ellipse. And it cannot intersect the base. If it does, that's a parabola. But in this case, it didn't intersect the base, and it forms an ellipse around its intersection with the cone. Like so. And so the key features of the ellipse is you should definitely know the two foci. There are two, foci. I looked it up before making this video. It's pronounced foci when it's plural. Yeah, I'm proud of that. There are two foci of an ellipse. And what an ellipse is, actually, the definition of an ellipse is it's all the points for which the sum of the distances to those foci is constant. And what I mean by that is, for example, let's say I had a point P right here. This distance, let's call this focus A and this focus B, which is not the conventional naming, but whatever. PA plus PB is going to be constant as this point travels around. So let's say we had a point here, and this is Q. Well, we also know that QB plus QA is going to be the same length because the sum of the distances to the foci is constant. It stays the same no matter what point you're at in this ellipse. And another interesting thing is that the sum of these distances is actually the length of the major axis. And we say that by saying that the sum of the distances is equal to 2a. Let me draw this out for you. And you might be like, A, where did that term come from? Oh my goodness, I can do this. Okay, good enough. This is our center. A is actually this length right here. That's A. That's called the semi-major axis, and the length of that is called A. And so naturally, the whole major axis is going to be 2A. The length of that is going to be 2A. Similarly, there's a minor axis, which is perpendicular to the major axis and also goes through the center. And the minor axis has a length of 2b. And you guessed it, the semi-minor axis has a length of b. And from here, it's actually simple to find the focus. The focus is always on the major axis. It's going to be somewhere on this axis. And the distance to the focus is called c. And how we can find C is by one of the ways we can find C is by knowing the relationship between the length of the major and minor axis. Because we know that C squared equals A squared minus B squared. And in the standard form of an ellipse, which I hope you've learned. If not, maybe watch a video on that first. In the standard form of an ellipse, it's x minus h squared over a squared or b squared, depending on whether it's a horizontal or vertical ellipse. But it gives you a squared and b squared in the equation, so that's really nice because all you gotta do is subtract b squared from a squared, and take the square root of that, and wow, that gives you the distance to your focus. An ellipse also does have two directrices, and I will explain that in a moment. And actually, I'll explain this using a horizontal ellipse, because remember, these rules apply for both horizontal and vertical ellipses. But if we have our center there and our two foci right here, we're also going to have two directrices, not like a parabola this time where there was only one. In an ellipse, there's two, because there's one directrix that corresponds with each focus. And something really interesting about the ellipse is that for every point on this ellipse, not only are the sum of the distances to the foci constant, but there's actually a specific ratio of distance from the focus to the directrix. So let's say, for example, this was a point P, and it was, let's say, 2 away from this focus, and it was 5 away from this directrix. So the ratio of the distance from the point to the focus and then over the distance from the point to the directrix is equal to 2/5. But then when we have this other point right here, let's call it Q, let's say this distance is 4, and this distance, it's going to be 10 because that ratio is always constant, right? That's really interesting about every point on this ellipse. But it is important to note that the ratio is going to be from the focus to its corresponding directrix. Like, I can't take the distance from here, say that's 4, and then expect this distance right here to be 10. No, that's not how it works. It's got to be the corresponding directrix. And if you recall, in the video about parabolas, that ratio at any point on that parabola was 1. But in an ellipse, it can actually be, that ratio can be anywhere that's less than 1, actually. And this ratio is called the eccentricity. So for this particular ellipse, the eccentricity would be 2/5, but the eccentricity for an ellipse just has to be less than 1, and it's an ellipse. And it can't be negative, but it has to be less than 1, and that makes it an ellipse. But now you might be thinking, well, how do I find, like, what is the distance to the directrix? Well, from the center, the distance to the directrix, let me do this in a different color, is actually A over the eccentricity. And then the eccentricity is also equal to C over A, which is important, which is good to know. I'm sorry, I'm hitting you with so much information, but this is just analytic geometry information, all in, like, most of it all in one place. So at least for mu alpha theta, at least. So A over E is equal to C over A, right? So this is just A over C over A, which becomes A squared over C. So the distance from the center to the directrix is just A squared over C, which means in this case, when the directrices are vertical lines, and you know they might not always be vertical lines, they might be horizontal lines, but in this case, when they are vertical lines, the x-coordinate of the directrix is just going to be the coordinate of the center, the x-coordinate of the center, plus A squared over C. And that's how you find the equation of the directrix. One last thing, I am going to cover the lattice rectums, because even though that's really not as important, they still do come up on tests sometimes. So if you recall from the last video, a lattice rectum is a chord that runs through the focus of a conic section, is perpendicular to the major axis, and its endpoints touch the conic section. So these would be the two lattice rectums of our conic. And as you can see, since they go through the focus, it's pretty easy to find their y-coordinate, right? It's the same y-coordinate. This distance is C, and it's the same y-coordinate as that focus. But if we were to find the x-coordinates of their endpoints, this one would be negative b squared over a, so it would be b squared, so it would be, let's say, h minus b squared over a as the x-coordinate, and then the x-coordinate here would be h plus b squared over a because it's to the right, and then the y-coordinate. But usually what I do if I'm trying to find the endpoints is I'll just plug in into this standard form equation. I'll plug in c for y. I mean, like the y coordinate of c for y, and then I'll solve for x. But if you need to know this like right off the top of your head for a team round or just something fast, it is good to know that the length of the lattice rectum is, the whole thing from here is 2b squared over a. Now we're going to go over circles, which are a very special case of an ellipse. And the cool thing about circles is that, one, there's like the least amount of information compared to any other conic. But in terms of the plane intersecting the cone, the restriction is it's just like an ellipse, right? The plane cuts through one cone and it can't cut through the base. But there's a catch. The plane has to be parallel to this base, right? So, like for example, if this, oh my god, that was definitely a straight line. If this line right here was perpendicular to the base, it would also have to be perpendicular to that plane because it has to cut at an angle parallel to that base. And only then will it form a circle. And you can kind of see that, right? Because the base is a circle, and as you kind of push this base up, you just keep getting smaller and smaller circles. And that's exactly what happens when that plane cuts through that cone and we get a cross section of it. It's going to be a circle. Circles are nice. They're really nice. Just pretend that's a perfect circle. It actually wasn't bad for my illustrations. And then we know that circles have a center, and circles are just, a circle is the locus of points. That means it's all the points. It's the locus of points for which, the locus of points that are a constant distance away from that center. And that constant distance is just the radius, right? So all of the points that are a distance of r away from that center, those are the points in that circle. It's as simple as that. And so usually, if you've noticed, the focus is the most defining point of our conic, right? Like the relationship of the distances between points and that focus largely determines most conics. And in this case, it's the only thing that determines this conic because the center of the circle is actually its focus. And then you might be thinking, okay, that's cool. What about the directrix? What about the latus rectums? And that is a great question. But the thing is that like the directrix and the latus rectum aren't really that important in the circle. Like sure, technically it does have a latus rectum and it does have a focus. I mean, it does have a directrix. But it's really not that important. As you can see, the only thing that matters is the focus. And so one interesting thing is, you know how I said earlier that in an ellipse, the eccentricity has got to be less than 1? If I didn't write it explicitly, but let me say it now. It has to be less than 1. And it can't be negative. Because that's the ratio of the distance from the point to the focus and the directrix. Well, an interesting about circles is that E, the eccentricity of the circle, is actually equal to 0. That means the ratio of the distance from the point, any point on that circle to the center, the radius, essentially, the radius over the distance to the directrix has got to be 0. But the radius is certainly like a finite amount, right? Like if the radius was 5, how could 5 over the distance like let's say the radius was 5. How could 5 over the distance to directrix be 0? Well, if this doesn't make sense, just ignore it. But the only way that's possible is if the directrix is a line at infinity. So the directrix is just a line that's infinitely away. Because I don't want to tell you that the directrix doesn't exist because that's technically not true. But the directrix is just a line so far away. It's infinitely far away that the eccentricity becomes 0. Because the focus is just infinitely close in a comparison. So that's the directrix. And the latus rectum of this shape is just really just any diameter of the circle is a latus rectum, right? That makes sense. It goes through the focus and it touches the circle at both endpoints. So a diameter is the latus rectum. But again, they don't really matter. All that matters is the focus, right? The focus and the radius. That's all that determines a circle. Anyway, I hope you thought that was interesting, and I hope I didn't bore you too much. But there we go. There's the second installment of the conic definition series. Bye-bye.